Hello. Good afternoon. The NBA series is tied up now. Miami looked good last night. And in class, we're talking about utility theory. So let's go on with utility theory. We'll see where we are. We're talking about utility theory and risk aversion. And this is a very interesting area that has applications far and wide, much wider than that for financial engineering. Now, some of you may have known some things about utility theory. So if you have, just bear with me. Let's see where we're at. Where we were at the last time was we were starting a numerical example. Let's first give three axioms of utility theory. Now, when we talk about utility, decision theorists call this utility, call this when we have probabilistic outcomes. Otherwise, in deterministic cases, in certain or deterministic cases, they talk about value functions. Talk about values instead of utilities. However, economists, if you look at the economists, call both cases utility. Okay, so economists call everything utility, whether it's deterministic or probabilistic. Decision theorists make a distinction between the deterministic case, where they talk about value functions, and the stochastic case, where they talk about utility functions. That won't be too important for us, but let's do this. Okay, let's give our axioms of utility theory. These are three axioms that we can base utility theory on. Other treatments may have more, or actually most would have more axioms than this, but these are enough to state our things. Okay, it says preferences can be stated and this is something we call completeness. And let's say what we have. Given a choice between A and B, either one, we prefer A to B. These don't have to be in dollars or numbers. A could be apples and B could be bananas, if you like. Just a choice between two objects. Or 2, apples are not as good to us than bananas. Or 3, we're indifferent to a choice between apples and bananas. This is strict preference. Now, what we mean that they can be stated, they must be stated. We can't say if we're given an apple and a banana and we're asked to choose, we can't say, oh, I don't really know what I like better. You have to make some choice. You have to say one is better than the other is better than that one, or you like or dislike either of them the same. And then we say and are transitive. And this transitive, we could call this order preserving. Okay, so what do we mean by that? We'll say that if A is preferred to B and B is preferred to C, then it must be true that A is preferred to C. Otherwise, we flip-flop. So if you like, if an apple is better than a banana and a banana is better than a cantaloupe, then it best be true that we like the apple better than the cantaloupe. Of course, these objects are different in size, so we would have to take a piece of cantaloupe, say a slice. Likewise, when we talk about being indifferent, if we're indifferent between apple and banana, we like or dislike them the same, and we're also indifferent between bananas and cantaloupes, then it must be true we must be indifferent between apples and cantaloupes. Let's cross these C's. Okay, so that's transitivity. Everybody has to have this axiom that you're complete and transitive. Now, axiom 2 is kind of obvious. It says that if we prefer apples to bananas. Then the lottery. We'll take a lottery here. Let's call this lottery L star. And let's call this P star A. And this is A. And this is B. And this is 1 minus P star A. Is preferred to the lottery and we'll have a lottery L, and we'll call this P of A, probability of A, and 1 minus P of A, B, if and only if and sometimes we abbreviate that as IFF, that P star of A, the probability of getting A in the first lottery, is greater than P of A. Okay, so this is an inequality sign, not a preference sign. Okay, now the axiom we're going to use to construct we will use to construct cardinal or numerical utility functions is as follows. This is our axiom 3. Axiom 3 says the following. It says, if A prime is preferred to B prime is preferred to C prime, again, we could consider these apples, bananas, and cantaloupes, if we like. Then there exists, and let's call this axiom the continuity, because that's what this axiom is. It's a continuity axiom. Then there exists which we said that we could use this math symbol for it, a probability P for outcome A prime, such that the decision maker, and we'll just call it DM, is indifferent to a choice between the following lottery, L, Here's P, and here's 1 minus P. A prime, C prime. So A prime is the best possible outcome. C prime is the worst possible outcome. And receiving B prime with certainty. Okay. Okay, so B prime, you could think of B prime as like a fair price for that lottery. Here. Now let's look at our example again. Oh, and also let's say the following. This also implies something else. Okay. Then we're going to say that the expected utility of B prime equals the expected utility of the lottery. Okay, what is the expected utility of the lottery? It's just P times the utility of A prime plus 1 minus P times the utility of C prime. Okay. And the expected utility of B prime is what? It's just the utility of B prime. The expected utility of B prime is just the utility of B prime. Because remember, B we get with certainty. So the expected utility of a constant the expected value of a constant equals a constant. It just equals that constant. So this is the equation we're going to use. We're going to say that the utility of B prime equals the utility of that lottery. Okay. Now let's see how to use axiom 3 to construct a utility function. Axiom 3 to construct a utility function. And of course, this can be a cardinal or a function or a numerical function here. Okay. In our example, we had the following. Our example, we had the following. We had action or lottery, if you will. And we had 1 and 2. We had 2 possible lotteries. And an outcome we had A and B, and we could say A equals heads and B equals tails. Okay, so you had 2 equally likely outcomes here. Under the first lottery, we win $10,000 if we get ahead, but we lose $5,000 if we get a tail. Whereas in our second lottery, lottery 2, we win $4,000 for a head, so we win less than half of what we would win in lottery 1. But instead of losing money on a tail, we simply break even. So we don't gain or lose any money. So most people, most decision makers would pick lottery 2. Even though the expected value of lottery 1 equals $2,500, which is greater than the expected value of the second lottery, equals $2,000. Okay. So now we're going to see why. Okay. Why is this true? We're going to see this is because of risk aversion. Okay. Okay. So let's try to specify a utility function for this example. For this example. And what we're going to do is, before we specify that, we're going to note the following, and this is important. If the 3 axioms are satisfied, then maximizing expected utility is always optimal. Okay, this is an important thing about utility theory that was first discovered by von Neumann and Morgenstern. Okay, now let's let the utility of $10,000 equal 1. Arbitrarily, we'll just let it equal 1. Utilities are totally arbitrary. We could have let it equal 100 if we like, or we could let it equal pi. And the utility of $0 equals 0. Okay. Now, we have to determine the utility of $4,000 and the utility of minus $5,000. Those are the only two things we have left. Okay. Okay. So let's first look at the utility of $4,000. Utility of 4,000. Okay. So we're going to set up an example. We're going to pose the following question. Consider at what probability that you would be indifferent to a choice between the lottery and we'll call it L, and this is our lottery that was L1. This lottery says you win $10,000 with probability P, and with probability 1 minus P, you win $0. So this equals A prime, this equals C prime, and receiving B prime equals $4,000 with certainty. Okay. Now, let's look at the interpretation of this. Let's interpret this. This interpretation will make this specification of P easier. The interpretation says at the following. Say that you currently hold a ticket to the lottery L. L. Did we say this was the lottery? Yeah, good. And someone comes along and offers to buy it from you for $4,000. Okay. Now, if P was high, you would not accept this offer. But as P comes down, this offer seems more and more attractive to you, because the expected value of that lottery is $5,000. But you could also get 0 at that. You could get either 10,000 or 0. Now, how high would P have to be for you to turn down this purchase offer? Okay. Okay, typically I ask somebody in class to give me an answer, but let me answer myself. So we have nobody sitting in class right now. Say that P say that P equals 0.6. So it's a little more than 1/2 here. Now, use the axiom 3 to calculate the utility of $4,000. Okay. That is, we solve the following. We say that U of B prime equals P U of A prime plus 1 minus P U of C prime here. Let's make sure that we said that. Yeah, we already said that. Good. So we say that U of 4,000, that's our B prime, because that's the price, equals what? Equals 0.6 U of A prime. A prime is the 10,000, so its utility is 1, plus 0.4 times the utility of C prime. C prime is 0, so the utility of that is 0, we said. So this equals 0.6. So let's plot that then here. Okay, let's plot dollars here and utility here of dollars. Okay, so we know, what do we know? We know that at $0, our utility is 0. And at $1, at $10,000, what is our utility? It's 1. So let this be 1. And this is $10,000. Okay. Now we just calculated that the utility of 4,000, which is 4,000 about here, is 0.6. So So let's go up here and come across, what would that be, 0.6. And this would be 4K. So what we see is that we have a function that is concave. Remember we said that concave functions look like caves, right? I have that written down here. Let's do this then. Okay. Recall we said that concave functions, this is the easy way to remember it, look like caves. And that is not as silly as it sounds, because the etymology of the word concave comes from the Latin cavus for cave, cave-like. We can give a definition of a concave function is the following. We'll say a formal definition is as follows. It says that f of lambda a plus 1 minus lambda b is always greater than or equal to lambda f of a plus 1 minus lambda f of b. Okay. Now this is equation 9.2, page 231. Let's state this in words instead of this. Let's say, simply stated, a concave function is always on or above the straight line segment between any 2 points we'll call these A and B on the function. Why don't we call these f of A and f of B. Okay, let's draw a picture. So we just say that that concave function always lies on or above that. So this is what we mean. Let's draw a picture of a concave function. Let's say x, f of x. Okay. Now, let's take a function that goes like this. Okay, let's take 2 points on that function. This is A. This is B. And this is 2 points on the x-axis here. And let's draw the straight line between f of A and f of B. And what we're going to see is the following. Let's take a point halfway between A and B. So let's call this point lambda A plus 1 minus lambda b for lambda being approximately 1/2. Okay. The way I drew it is not, it could be a little more to the right, but that's okay. Now let's look at this. This is what is this point here? This is the point of what? This is lambda f of a, because this is f of a, and this is f of b up here, plus 1 minus lambda f of b. Okay? Whereas, what is this here? Let's look on top. Where we went on the curve, what do we have? Now we have the point of what? We have f of lambda a plus 1 minus lambda b. And so we have the following. So we can see that curve always lies on or above that straight line. It lies on it at A and B, exactly. But every place else, it's strictly above that. So what do we have? We have exactly the definition. We say that f of lambda a plus 1 minus lambda b is always greater than or equal to lambda f of a plus 1 minus lambda f of b for, this is for all lambda greater than or equal to 0 and less than or equal to 1. Okay. This lambda a plus 1 minus lambda b is, this is nothing more than the equation of the straight line segment between A and B. Okay. So that's the equation may look a little complicated, but it's not complicated at all. All it says is that our function must lie on or above the straight line between any 2 points on it. Now, let's do the following. So, if f of x or in our case, u of x, the utility, is differentiable then we have the following. Then f of x is strictly concave if and only if f prime prime of x, the second derivative of x with respect to x, of f of x with respect to x, is greater than 0. And this is for all x. Okay, so let's look at this. Let's look at a concave function. Let's just make this greater than 0, because it's strictly. Let's take a function here. We'll call f of x, and we'll call this guy x. So this is what we've done before. Why do we want it greater than 0? Actually, we want it less than 0. Here's a concave function. The tangent starts off very positive, then gets less positive, goes to 0 at the maximum point, and then starts going down here. So the tangent, which is the first derivative, is decreasing. And this implies that f prime prime of x is less than 0 here. If it's always decreasing, the second derivative shows that it must be less than 0 because the first derivative is decreasing here. So this gives us an easy way to see if the utility function is concave. Now, why is this important? We could say, who cares about this? The important result is the following. Let's say a decision maker is risk averse if and only if the decision maker's utility function is strictly concave. Now, the decision maker's utility function should also be increasing. It should be increasing and strictly concave. Hopefully, it's differentiable too. It has to be continuous, but it should be differentiable too. Okay, now let's continue on with our example. As we saw for positive money, we were risk averse. Now let's calculate U of minus $5,000. Okay? Okay. Okay. Let's consider, to do this, we're going to consider at what probability P would you be indifferent to a choice between the lottery let's call this lottery L prime, because we called the last guy L. And this lottery has the following. With P, we get $10,000. So this is our A prime. With 1 minus P, we get minus $5,000. This is C prime. And receiving B prime equals $0 with certainty. Okay. So what we have here is the same kind of interpretation. We have the following. Okay, interpretation. You hold a ticket to lottery L prime. Now, lottery L prime has, as the worst case is that you lose $5,000. You can win $10,000 or you can lose $5,000. And somebody comes along and offers to take it off your hands or buy it for $0. Okay, so they just come along and say, listen, I know you don't like that idea that you may lose $5,000. So I'll just take that ticket from you. Okay, if P were high enough, why don't we say was high enough, you would refuse to give the ticket up. Okay, so we're going to say that how high would P have to be so that you would keep this? So how high would P have to be so you would keep the ticket? I say you would not give up the ticket. Okay. Okay, so if P is very, very high, you wouldn't give up the ticket, even though you have a chance of losing 5,000. So let's say P equals 0.9. Okay. So at 0.9 or above, you'll say, no, I'll take my chance because I have a very, very good chance of getting 10,000 and a small chance of losing 5,000. Okay. So now we solve for U of $5,000 again. And we get the following. We get U of 0, because this is B prime, equals what? Equals P 0.9 U of 10K, 10,000, plus 0.1 U of minus 5,000 here. Okay, and that's what we're looking for. So, okay, let's solve this. We know U of 0 equals 0. U of 10k equals 1. So what do we get? We get that U of minus 5,000 is equal to what? Equals 0.9 over 0.1 equals, and this is a minus sign, minus 9. So what we see on the negative side, if we plot this on the negative side, we get something like the following. This is $0, U of dollars. Okay, so on the U of 0 equals 0, and then what do we get? We get that U of minus 5,000, this is minus 5,000, equals minus 9. So say that's about here. This is minus 9. So now, again, this is concave. In fact, it's really bad here. So we're risk averse. In fact, we're more risk averse on the for losses than we are for gains. Okay. I think that's about it for today. Wait, we have a second. Let's talk about one other thing, if we have it. Another way to talk about risk aversion, another nice definition of risk aversion is the following. You are risk averse if you prefer the expected value of a lottery to the lottery itself. In other words, you would rather get the money than play the lottery. Okay. I'll go over that again here. In fact, you can see that the expected value of these lotteries are very small here. Okay. So you always prefer the expected value, the certain thing, to the probabilistic thing. That is I think that's a nice qualitative definition of risk aversion. Okay. Have a good weekend. We'll see you Monday.